It is a pleasure to be here. Those of you who've heard me speak before know that I like to start my talks with a confession. But I'm kind of intimidating doing that in front of 300. I like to do that one-on-one. I guess I have to remind myself of the American proverb, the more you confess, the more books you will sell. Anyway, I always thought that in my teaching, I was able to educate people in such a way as to promote innovation. I'll tell you today a little bit about how I discovered that that was not the case. And I'm sure you've read many newspaper articles about how we fail to promote creativity and innovation. So before I dive into my approach to teaching, I thought it would be good to perhaps look a little bit about what innovation is. And I'm going to use an example. And as example, I'm going to use this person, a colleague of mine by the name of André Geim, who won the Nobel Prize in Physics in 2010 for something called graphene. You've probably heard of graphite, which is, the stuff that pencils are made of. Graphite consists of layers of carbon atoms that are very loosely bonded to each other, which makes them peel off easily. So when you actually move your pencil over a piece of paper, it rubs off that carbon onto the paper. That's how you can write, one of the oldest known forms of writing. Well, he developed a method to pull off a single layer of these carbon layers, called graphene. The way he did that was by taking Scotch tape and putting some graphite on it, then taking another piece of Scotch tape, gluing it on the other side, peeling the two apart, and repeating that process over and over again until eventually it was left with one layer of carbon atoms. You may have heard of nanotechnology. This is nanotechnology. It's nanotechnology on a nano budget. All you need is a roll of Scotch tape. It's phenomenally inventive, and I think there are very few Nobel Prizes that have been given away for something so incredibly simple, yet so important. Now, what really distinguishes him is not this work, but the fact that he not only won the Nobel Prize, he also won the Ig Nobel Prize 10 years earlier. I don't know how many of you know the Ig Nobel Prize. It's given out at Harvard University. One of the people who is part of the award ceremony is a Nobel laureate, a friend of mine, Dudley Hirschbach. The award is given for science that first makes people laugh and then make them think. I was just looking on my phone for some examples. So here's one from last year, a bra that you can convert into 2 protective face masks. Or here, a prize in physics from 2 years ago, which was given to a team from France and the Netherlands, based on a paper entitled, which appeared in a peer-reviewed journal, and I'm reading to you the title of that paper, Dizziness in Discus Throwers is related to motion sickness while spinning. I'm not making that up. And what did André Geim win his Nobel Prize for? He won it for levitating a frog. Actually levitating a frog. So he's, as far as I know, the only person who won both a Nobel Prize and an Ig Nobel Prize. And it's actually very interesting to read his interview on the Nobel website, because in that interview, he describes what brought him to levitating a frog and discovering graphene. And he writes, or he says in that interview, for me, it's very boring to work on the same thing year after year. And in order to combat that boredom, what he does is he encourages his students to try out wild new things. In his words, graphene resulted from Friday night experiments where you try something very elementary and try to go in another direction. So it's basically a matter of, sticking out your neck in a sense, taking a risk, trying something. So the question that I would like to address today is, how can we foster or maybe even teach innovation? How can we push people's creativity? And, in case you doze off, but I'll make sure you won't, the answer to that is that we really need to teach real problem solving. Now, many of you will say, that's exactly what we do. But I will point out that there is a difference between real problem solving, which is why I have it in italic there, and the problem solving that we actually train our students to do on our assessment. And secondly, we need to encourage risk-taking. Now, you all have a little clicker. It looks a little bit different from the one that's on there. It doesn't have that little window. There's no on-off button. It's already on. Since you're educators, I'm going to show to you what it looks like from my perspective as instructor here. I'm going to bring up the little window. Why don't you press a random button, except the channel button, because they should all be set to the right channel. So press 1, 2, 3, 4, 5, or whatever you want. As you press, you will see that this count here, I cannot get to the button, but if you look carefully, you can see here that the number goes up with 220 people who have clicked. Now, I'm going to ask you questions later. If you press 2 because you think 2 is the right choice, and then you change your mind, you think, oh, no, it should be 3. And you press 3, the 3 will override the 2. You don't get to vote twice, okay? So if you're already pressed and you're wondering why that number doesn't go up, it's simply because your vote has already been recorded. At any point in time, I have this little floating window that is in front of my presentation software. At any point in time, I can press on this button and see the distribution of answers. As you can see, many of you like button number 5. Now, why don't you all press number 1? Go ahead, press number 1. Very good. I like that you're following my instructions. Very good. Number 1, please. And you see that the distribution immediately changes. Go ahead, press number 5 again. You're great. I mean, with my students, I never managed to do this. As soon as I press this stop button here, it stops the polling. Now, if you press, nothing will happen anymore. The distribution is frozen. The software does one other thing at the same time. It grabs a picture of whatever is on the screen. So when I get home tonight, I can see, oh, they all pressed number 5 when I was on this screen. So that allows you to review it. It works with any software. You can have a Word file, PowerPoint, Keynote, whatever you want. It doesn't matter. Very simple, but I think that's the important part because we don't want to get distracted by technology. Turn the clicker around for a moment, and you'll notice that there is a barcode. You may think that your responses are anonymous. No, they're not. Each clicker has a unique ID number. Now, of course, I don't know which ID number you have, so you can relax, and it will be anonymous today. But basically, if I were interested in individual responses, I could have, when I gave you that clicker, asked you for some identifying information, and you could track individual students' responses. Okay, so we'll use these. Initially, we'll use them not as a pedagogical tool, as a survey tool. Later on, we'll use it as a pedagogical tool. It was mentioned in the introduction that I developed peer instruction about 20 years ago. This was before clickers. And the clickers were developed actually in my classroom. We started with a wired system and then took off on their own. And what I've noticed is that many people apply this technology incorrectly. They use it more as a survey tool, as a sort of a wake-up tool, than as actually an engagement tool. So I'm going to demonstrate to you how to actually use this as an engagement tool. I was really completely focused on the pedagogy initially, and then when the clickers took off, some people would come to me and say, oh, I've adopted your clicker technology. And I'd get really upset. First of all, because in my eyes, it's the pedagogy that matters, not the technology. But more importantly, I missed the boat on commercializing these clickers. Anyway, so today is an e-teaching day. I really wish the day would have been called e-learning day, because the emphasis should really be on the learning, not on the teaching. What matters is not what the teacher does in front of the classroom. What matters is what is happening in the minds of the learners. So I would like to start today with a little reflective exercise. I want to make you reflect on your own learning. And I would like you to think of something, and ideally take a little piece of paper so that you can actually write that down. I would like you to think of something that you are really, really good at, something you're proud of, something you know other people admire you for, and ideally something that has helped you advance in your career. It could be anything. It could be solving partial differential equations. It could be interpreting works of art from the Renaissance. It could be something mundane as baking pumpkin pies, although it's unlikely that that has advanced your career unless you're a baker. But, or it could be public speaking. You know what I mean. So, and you're all successful individuals, so it shouldn't take too long for you to come up with something. You won't have to reveal it, don't worry. So write it down and then fold it up so that nobody can see what it is. But I do want you to commit to something, right? And if you're asking me, one thing only? Yes, one thing only. I know many of you have been very successful at many things, but I want just to pick one. Does anybody need more time? No? You're in trouble if you would need more time here. Okay, good. So now that you have committed to something in your mind or on a piece of paper or on your electronic device, now comes the hard question. The hard question is this: how did you become good at whatever it is that you wrote down? What were the circumstances that led you to develop this skill or knowledge or ability? And the things that we're good at, we usually enjoy, and we usually are not aware even of how we learn it. So this might be a hard question. It might be hard for you to dig back in your mind and reconstruct how you developed it. So I'm going to give you 20 seconds, and I want you to write down a few words describing how you became good at whatever it is that you wrote down. And I can see a lot more pensive faces now. It's not that obvious, huh? I've done this all over the world. I've done it in Asia, Korea, Japan, China, Taiwan, Thailand. I've done it in Africa. I've done it in South America, in Europe. And I've collected the responses. There are no cultural differences. We all learn the same way. Let's see if it's different at Boston College. I've basically taken the answers that people have written down, and I've categorized them, and they fall into 4 different categories. I learned by trial and error, by trying out things and then making mistakes and learning from the mistakes. I learned from it in lectures, or I learned from it by practicing, or I learned by apprenticeship, by tagging along with somebody who is really good at it and, looking over that person's shoulder and then learning from her or him. And then there's a series of other categories which I've lumped all together, like family, friends, and so on. I would like you to choose what you think comes closest to whatever it is that you wrote down and press a button between 1 and 5. So go ahead, enter what comes closest to what you wrote down about how you learned that important skill. And this is an important skill. I asked you to choose something that advanced your career. Okay, so let's see if it's any different from anywhere else in the world. And no, it's not. The biggest bar is practicing. We learn by practicing. We learn by doing. And in a sense, you could say answer number 1, trial and error, is also practicing. It's just another expression for the same concept. So you learn, this will come as a relief maybe, but you learn no differently from anybody else all around the globe. But that's not why I did this little exercise. I did it because there's something else absolutely remarkable about this distribution. What is it? Lectures. Only one or two poor souls here chose lectures. And how do we teach? This is how we teach. Right? Only two among all of you said they learned that really important skill in lectures. Yet 99.9% of all teaching takes place in learning spaces that are no different from this one. This is a picture of me teaching my pre-med course when I was still an assistant professor. This picture was taken BC, before computers. Right? I'm still using an overhead projector there. And, this is nothing new. In fact, when I started teaching at Harvard, I never asked myself, how am I going to teach? The question did not even come up in my mind. Now, that's strange, right? Because when you start doing something new, the first question you should ask yourself is, how am I going to do it? The question didn't come up in my mind. I was going to do to my students what my instructors had done to me. I naively thought, this is how I learned it, and therefore this is how I'm going to teach. So, I started teaching that way, and very quickly I got signs that what I was doing was the right thing. What are the metrics? And I had been asked to teach physics to pre-meds. These were not students who were taking physics because they wanted to learn physics. They were taking physics because they had to learn physics. Most of my colleagues, I didn't know that when I accepted this assignment, refused to teach that course. Because at the end of the semester, when they got their evaluations, they would come close to committing suicide. But not so for me. I got a 4.5 or a 4.8 on a scale of 5. So clearly the students liked what I was doing. On top of that, I could give these students some really, really hard problems. Problems I wasn't certain I could solve under the pressure of time. But they did well. So they did well on what I consider difficult problems. They gave me high ratings. Obviously, I was doing the right thing. Now, in retrospect, there were always some worrisome signs. But, I'm a positive thinker, so if there are positive signs and negative signs, I'd like to focus on the positive ones and ignore the negative ones. Let me give you some example. Some students, in spite of giving me high ratings, would write down at the bottom, physics is boring, or physics sucks. I could never make any sense of why somebody thought of physics as being boring, so I simply ignored them. Let's talk briefly about the history of learning spaces, given that we're in an auditorium. In 3 slides, 3 seconds, I can give you the history. This is almost 3,000 years ago, the Greek invented the amphitheater. The Greek, incidentally, were smart enough not to use this for teaching. This was for performances. If you've ever seen an illustration of the School of Athens, you don't see people sitting in benches, but, you see people walk and talk in pairs to each other. Okay, let's ignore that for a moment. Let's go fast forward to the 18th century. And here we're in the 21st century, which is the classroom in which I teach now. So given that everybody is teaching that space, I would like to spend the first part of my talk to talk a little bit more about education. What is it exactly that we're trying to accomplish in this setting? And is it really the most appropriate thing that we're doing? After that, I'd like to talk a little bit about peer instruction, which you heard about before, but you might not be familiar about, which is what I do now after discovering that my students weren't really learning in this environment. And in order to keep you awake, we'll end this with a test. So you better pay attention. So let's start by asking ourselves the following question. What happens in a lecture? Let's go back to that picture of me teaching my pre-med class. I want you to describe to me in 1 or 2 words, and ideally using a verb, the activity that is taking place on the screen behind me. And the two verbs I do not want to hear are teaching and learning. So you have to find another way. So go ahead. Performance, sitting, listening, telling, frustrating? Oh, illustrating. Yeah. Sleep? I mean, my students are not sleeping. You know, I recently heard a wonderful quote from the French writer Albert Camus. He once said, "Some people talk in their sleep. Lecturers talk while other people are sleeping." But you know, my students are not sleeping. Notice that a lot of these verbs, sitting, sleeping, performing, pertain either to the students or to me as the instructor. Can we find something that describes the whole process? Transmission. In fact, I think that's on my next slide. No, it's sort of on my next slide, not the actual word. Lectures focus on transmission. Transmission of what, by the way? Knowledge. But what is knowledge? I mean, knowledge is sort of a very fuzzy word, right? Facts, content, information. Lectures focus on the transfer or transmission of information. And you know what? My students had rubbed that in my face very early on in my teaching career, but I had ignored it. I told you a moment ago that when I started teaching, I never asked myself, how am I going to teach? What was the question you think did come up in my mind? What, exactly, or more precisely, what book? So I went to a colleague who had taught this course before, and I asked him that question, and he said, oh, in this course we're using Halliday and Resnick. So I was told that in the US, students buy the book that goes with the course. I was educated in Europe, as you heard, and there, we'd never buy books for introductory courses. I mean, why would you buy a book if the professor is presenting it to you? Right? So I went to the Harvard Coop, the bookstore in Harvard Square, and I made sure that they had 150 copies of Halliday and Resnick in the bookstore. And as I walked back from the Harvard Coop to my office, I said, wait a minute. If the students have the book and I have the same book, then what do I do in the classroom? So I stopped at the office of my colleague and knocked on his door, and I asked him that question. And he said, don't worry, there are lots of different physics textbooks. And he pointed at a shelf full of different physics textbooks. And I started looking, and very quickly, I found the perfect book. It was perfect for two reasons. One, it had a different approach than the book that the students bought. But that was not the important reason. The important reason was the book was out of print. They couldn't get their hands on it. So for every lecture, I spent 10 hours preparing lecture notes, and then during class, I would either project the lecture notes on the overhead projector or write them on the board behind me. And because my notes were different from the book, they had a slightly different approach, I decided to distribute photocopies of the notes at the end of the class to my students. Now, why do you think that I hand them out at the end of class and not at the beginning? Why? So they would come to class and listen to me. But if you stop to think about that, isn't that already admitting that there is a problem? I mean, if the students could get the information by just reading the notes, why not give it to them? That question never came up in my mind. But what did happen was that after a few weeks, some students came to me and they said, Professor Mazur, couldn't we get a copy of your lecture notes at the beginning of each class? This way we don't have to write down that much. And I had indeed noticed that each time I wrote A on the blackboard, 150 pens went A in the notebooks of the students. I once heard somebody describe the lecture as a process whereby the lecture notes of the instructor get transferred to the notebooks of the students without passing through the brains of either. Anyway, so I handed them out at the beginning of the class, and much to my relief, the students wouldn't just come in, grab the notes, and go back to bed. No, they came in, grabbed the notes, sat down, and they still copied everything because they had no time to read the notes. Well, that first year went by, I got my high evaluations, and you know what happens when you get a high evaluation, right? you get asked to teach a course again. You get punished, right? So my colleagues asked me to teach a course again, and as I prepared for the second year, I said to myself, you know what? Rather than handing out these notes lecture by lecture, or class by class, I should say, what I'm going to do is a week before classes start, I'm going to send out the entire set of notes for duplication, and on the first day of class, the students get the complete pack for the entire semester. You know what the unexpected result was? The unexpected result was that about half a dozen students wrote on their questionnaire at the bottom in the comment section, Professor Mazur is lecturing straight from his lecture notes. Hello? I mean, what was I supposed to do? Develop another set of lecture notes to lecture from that was different from the lecture notes I gave out to them? I was livid. These ungrateful students. But you know, they had a point. I was focusing on information transfer. Now, given that I think it's fair to say that in 99.9% of all classes around the globe, that is what happens, we could ask ourselves the question, is that what education is? Is education just the transfer of information? Actually, now that we have these clickers, I hadn't thought about that before, but why don't we just poll you all? So if you think that education is merely, with the emphasis on the word merely, the transfer of information, press 1. If you think there's more to education than just the transfer of information, press 2. Now be honest, don't play games with me, even if it's anonymous. Okay, so we have about 200 responses there, so let's look. And I think that 3. Okay, whichever instructor wrote 3, you're in trouble. But those who pressed 1 are also in trouble. Because imagine that education was just the transfer of information. Why are we still giving lectures? I mean, you could put a camera in the classroom, videotape it, and make it available to the students for download. They can pull out their iPhones, iPod Touches, whatever, and watch it whenever they want. Let me ask you something. What would be lost by doing that? Personal connections, interactions. But let's face it, if you teach a large class like this, how much personal interaction is there? Have you ever asked the question, does anybody have a question? And you know what happens, right? The students look down, they don't want to make eye contact. There is no interaction. Will we gain something? Yeah, because we wouldn't have to lecture anymore. We can invest the effort once, and then for a couple of years until our clothing looks out of date, we can continue to use the same videotape. In fact, we could use the videotapes from somebody else at another university. What is more, the students can watch it whenever is most convenient for them, whenever they're most predisposed to actually learning. They don't have to do it at a particular time, in a particular block of time. If you want to watch 7 minutes, you watch 7 minutes. If you want to watch 10 minutes, you watch 10 minutes. There are other advantages. You can actually pause the tape and think. Can you do that in class? Can you say, Professor Mazur, could you please be quiet for a moment? I need to think. I don't think you can do that. Or if you need to go to the bathroom, you can stop the video and run to the bathroom. You can play it again to listen to it again. You can stop it and call up your friend and say, do you understand what Professor Mazur said at 8 minutes and 2 seconds? Right? That is not possible if you do this. So I think there has to be more. And given that 95% or whatever the percentage is, I didn't look, of you agrees, I have you in a corner now because you have to tell me what is missing. There's more to education, and what is it? Learning, reflection. Learning is I guess, a word that's too vague, right? We hide behind that word a lot of things.
Inspiration.
Inspiration, maybe, although the inspiration could come in principle from a lecture, but Practice? Of course, practice, right? Because we all agreed early on with that little survey that practice is important. Is there time to practice in the classroom? And what does practice do? What do we really want our students to do? We want our students to be able to do something with that information, right? Not just regurgitate the information back to us. So I think what needs, apply it to new circumstances or transfer the knowledge embodied in the information to a new context. Not that long ago, I was at the University of Connecticut giving a talk about education in the physics department. And one of the professors came up to me and said, I've worked really hard this year to bring physics in the context of the real world in order to make physics live for his students. And he said that the context that he had used was baseball. You know, there's a lot of physics in baseball. Runners running, trajectories of balls, collisions between bat and balls. So in the classroom, on the homework, on the midterm examinations, he had put problems that involved baseball. At the end of the semester, he was writing the final exam, and he realized he had run out of baseball problems. So he put some football problems on the exam. Professor, complained the students, we've never done any football problems. I'm sure you've had students come to you after your classes say something similar to that, right? And I think not being able to transfer your knowledge into a new context is the hallmark of not understanding. Shows that you've not assimilated that information, right? We want our students not just to be able to solve the problems we already solved. We want our students to solve the problems that we have not yet solved. I want my students to stand on my shoulders, not to just bring them up to my level. Anyway, so I think that important part is typically missing in the classroom. And what is the result? The result is, and usually I show data to back that up. I thought I'd make this talk interactive, and in order to make it interactive, I had to throw out the data. But if you look on my website, you'll find the actual data. Things that happen is that there is really lack of learning. So much of education, and we'll talk about assessment in a moment too, is simply the instructor delivering information to the students. You wait 2 months, you tell the students to put their books away, and then they regurgitate the information back to you. How did I learn history? Simply as a collection of dates. In I forgot, do you know when the Dutch defeated the British in the River Thames? I forgot, I'm sorry. So in some year, 1609 or whatever, the Dutch defeated the British in the River Thames. And, and then 2 months later on the exam, in what year did the Dutch defeat the British in the River Thames? 16 whatever. Now, I've forgotten now. Because, the mind does not remember facts very much. It would have been much more interesting to learn about the socio-economic factors that led to this conflict and why the Dutch were able to defeat the British on their home turf. But that was not what happened. It was memorizing facts, regurgitating them back. The famous psychologist Skinner once said, and I think this is really a quote that resonates with me, is education is what is left after all that is learned is forgotten. There's a lot of you, some of you are smiling. I think we should be crying about it because I don't think that's the most effective approach to education. I discovered this lack of learning only after teaching for about 8 years. I came across an instrument that measures students' understanding of the concept of force. Now, force is typically taught in week 2 of an introductory physics course, and everything else builds on top of it. And most of the students at Harvard have had already an AP, an advanced placement physics course. So I was just very quickly reviewing it. I was not actually thinking that I was teaching them force because I thought most of them had already learned it. At the end of the semester, when we were doing much more complicated things, I read about this instrument to measure students' comprehension of force, which claimed that most US students in California, New Mexico, Arizona at the end of the physics course, a semester-long course, didn't do any better than those at the beginning. I thought, no way. There must be some kind of a disease in the southwest of the US. Here up in the northeast, I'm sure we're doing better. I gave it to my students, afraid that they would be offended by the simplicity. And within 30 seconds, one student raised her hand and she said, Professor Mazur, how should I answer these questions? According to what you taught me, or according to the way I usually think about these things? I had no idea how to answer that question. And by the time the test had been completed, it was clear that my students had not even learned the most basic principle. There's also a lack of retention. As I just demonstrated, I don't even remember the date that I learned. And 1660, I was off by 60 years. Thank you. Long live the iPhone. Lack of retention of knowledge, if you want, but also lack of retention of students. We keep complaining about bleeding students who are interested in STEM disciplines because we're not keeping their interest. So, oops, pardon me. I want to stop this for a second. This reminds me a little bit of a clip that I saw a long time ago on Saturday Night Live, which I want to share with you. Here we go.
I find that education, I think it don't matter where you go to school. Italy, America, Brazil, it's all the same. It's all just memorization. And it don't matter how long you can remember anything, just so you can parrot it back for the tests. And I got this idea for a school I would like to start. Something called the 5-minute university. And the idea is that in 5 minutes, you learn what the average college graduate remembers 5 years after he or she's out of the school. With the cost of like $20. That might seem like a lot of money, $20 just for 5 minutes. But that's for like a tuition, cap and gown rental, graduation picture, snacks, everything included. You know, like in college, you have to take a foreign language. Well, at the 5-minute university, you can have your choice. Any language you want, you can take it. Say if you want to take Spanish, what I teach you is, ¿Cómo está usted? That means, how are you? And the answer is, muy bien. Means very well. And believe me, if you took 2 years of college Spanish, 5 years after you're out of school, ¿Cómo está usted? Muy bien. About all you're going to remember. So in my school, that's all you learn. You see, you don't have to waste your time with the conjugations, vocabulary, all that junk. You just forget it anyway, now what's the difference? Economics, supply and demand. That's it. Business is you buy something and you sell it for more.
Now you're all laughing, but I think we should really be crying because there is some deep truth to a lot that is in that little clip. This was, by the way, in the 70s. It was a long time ago, that clip. Another thing is, I think that assessment, the way we assess our students, I alluded to this earlier, promotes memorization and stifles creativity. Let's think about what a real problem is, right? If you have a problem, you know where you want to get. You know the outcome, right? Let's say you have a product. You want to make the product successful. There is no prescription for getting to a successful product, so you have to find how to make that product successful. You're baking a cake. Oh my God, there's no sugar. The supermarkets are closed. You got a problem. There's no prescription for solving that problem. So whenever you solve a problem, the key is to find the solution to get from the problem to a known outcome. And I want to emphasize, the outcome is known. The solution is unknown. Most of the problems that we give our students to solve do not follow this pattern. You have a problem statement, and the students apply a procedure to find an answer. And the answer is what we evaluate them on. The answer is, the procedure is known, and the answer is unknown. I discovered this the hard way when on an exam, because I didn't believe that result about the force. I thought that can't be. There must be some psychological effect going on. So I decided on my midterms to put two types of problems. One was a textbook problem, and the other one was a word-based problems on exactly the same context, circuits, for example. And I found that my students were able to do perfectly well on the textbook problem, but they floundered on the word-based problems, which to me was trivial. In fact, I had to fight with my colleague to put it on the exam because he thought we're giving away 20% of the exam. So students simply follow procedures and they don't understand the underlying reasons for those procedures, and therefore no wonder you don't become a real problem solver. In fact, I would say we live in an age where increasingly computers can do procedures. And real problem solving really is the finding of solutions. Unfortunately, and another point is this, which also has to do with the assessment, is that when you try to solve a real problem, there's not a straight path from problem to solution. You try an approach, it doesn't work. You try another approach, it doesn't work. You try a third approach, it works. Same for innovation, too. Take the light bulb. I started my talk with a picture of the light bulb for a good reason. Edison didn't just invent the light bulb. He tried. I think there were almost 300 failures before he finally managed to make a working light bulb. So there's no innovation that doesn't, and no problem solving that is not accompanied by mistakes and failures. It's impossible. However, the assessment is incompatible with real problem solving because the traditional assessment, one, focuses on outcome, not on process. It's the answer that matters, not how you get there. And more importantly, it discourages risk-taking. We only reward perfection. You make a mistake, you lose points. You get punished for it. Right? That's a big disincentive to stick out your neck and try something. It stifles creativity. There are two other problems with assessment. One, it focuses on the individual, not on the group. Yet just about any human endeavor involves groups of people. People in industry complain all the time. The graduates you generate don't know how to work together. Well, it is because we don't let them work together. We focus on the individual performance, not on the group performance. More importantly, the environment in which the assessment doesn't mirror anything that really happens. I'm sure you, just as I do, remember taking exams. You're put into a big hall, separated from each other so that you can't work together. Your book has to be put away. You're cut off from any source of information, cell phones, computers, you name it. And you're not allowed to consult anybody or any information. Has any of you ever encountered such a situation in real life? When I write a paper, there's nobody standing next to me, next to my desk, saying, you're not allowed to look up that paper from your colleague at Yale. You should have known that by heart. I can look up whatever I want. In this day and age, it's not about remembering information. It's about knowing how to use the information, how to find the information, how to vet the information. Yet I don't think that much of our assessment reflects that. So what should we do? Well, if we think about education, transfer of information is necessary. There's no question about it. But there's a second step, assimilation of that information. I've asked myself this question many times, where did that assimilation, I get it, where did that happen? Did that happen in the classroom while I was sitting, listening to my professors? No. It happened really outside of the classroom. In the classroom was a transfer of information, and the assimilation was outside of the classroom. Now, if you ask yourself, which is the hardest part? I think we'd all agree, especially in the information age, it's the second part, not the first part. So we should really focus on that second part, not on the first part. Right? So if you think of education as a two-step process where we put all of the emphasis on the easy part, leaving the hard part to the students on their own, we should really flip that. We should do the information transfer outside of the classroom and the assimilation of the information inside the classroom. So how do we do that? I mean, if you go to a business school or a law school, I think they already realized that a long time ago. The case study method, developed about 100 years ago, more than 100 years ago, at Harvard University, was probably the first example of the flipped classroom. Students read a case before coming to class, and in class, the focus is on the practice of the law, not the memorization and regurgitation of the law. But in a science course, that's still kind of heresy. Well, it turns out that the solution to my students not learning presented itself serendipitously. I told you about this test. My students were horrified after they saw the result, and they asked me to organize a session in the evening where I went through every single question of this test that tests the concept of force. And at some point, I came to a question which I thought was really trivial, and I made some sketches on the board, and in 2 minutes, I just explained the answer to that question. I didn't think there was much more to explain about it. I turned around, and I could at once see from the faces that they didn't understand it. So I said, does anybody have a question? They were so confused, they couldn't articulate a question. You know how it is, right? If you're really confused, it's hard to actually articulate it. I knew this was really serious because it dealt with one of Newton's 3 laws, which is, one of the most basic concepts in physics. So I erased the board, and I thought I better do it again and bring in some other concepts to, cement what I wanted to teach in place. I took 8 minutes. I gave the most brilliant explanation that I could come up with. And when I was done, I turned around triumphantly, knowing darn well that I nailed it this time, only to see that they still looked confused. And they still could not articulate a question. So in a moment of despair, I said, why don't you discuss it with your neighbor? And something happened I had never seen in my classroom. The entire classroom, 250 students, erupted in chaos. They forgot about me in front of the class. What's more, in 2 minutes, they figured it out. I had trouble believing that. I'd taken 10 minutes to explain to them unsuccessfully, and in just 2 minutes, they figured it out. But imagine 2 students sitting next to each other, Mary and John. John does not have the right answer because he doesn't understand it. Mary has the right answer because she understands it. On average, Mary is more likely to convince John than the other way around. But what is more, Mary is more likely to convince John than Professor Mazur in front of the class. Why? Because she has only recently learned it and still knows what the mental blocks are that John has. Whereas Professor Mazur learned it such a long time ago, to him it is so clear that he cannot even understand why somebody doesn't get it. It's what Steven Pinker calls the curse of knowledge. It's kind of an irony, right? Because you tend to think the more of an expert you become, the more qualified you are to teach. I'm sort of making the opposite argument, right? The more qualified you are, the harder it becomes to bring yourself back down to the level of a beginning learner. So I thought maybe I can exploit that in the classroom and basically ask my students to read the lecture notes before coming to class. They actually tell me what they found difficult. So in class, I teach by questioning rather than by telling. I talk a few minutes, put a question on the screen. Then I ask them to think about that question, just as I had you think about, how you learned. But rather than just polling them, I poll them and then say, now please discuss it with your neighbor. In fact, I tell them, and usually I only do this when the initial poll has between 30% and 70% correct answer, right? If everybody has it correct, then it doesn't make much sense to have them talk to each other. If less than 30% has it right, it's not going to go anywhere because there are not enough students who have the right answer. I tell the students also, and you will do this too in a minute, find somebody who has a different answer. So in other words, if you turn to your neighbor in a moment and the neighbor has the same answer, you say, thank you very much, and introduce yourself to the person in front of you, behind you. But you got to find somebody who has a different answer, okay? Students happily talk to other students with the same answer. I know that from experience, but that's not very helpful. Okay, so then I poll them again, and I explain, and then I repeat from the start. The crux of the matter, of course, is this discussion. Let me show you a little video clip about how that is in my classroom. So we have a rectangular loop that is placed in a uniform magnetic field in the direction indicated by these arrows. Don't worry about the question, okay? So the question is, what are the magnetic forces on the 4 different sides of this loop? So take a minute to think about this and then enter your answers. I do not want them to talk to each other, right? So it's individual answer. Please enter your answers. On my screen, I can see the answers as they come in. I do not show that
disagreement clearly here.
As you can see, it's a 50-50 split.
So turn to your neighbor and see if you can convince one another of the correct choice.
Right. It goes out of the page on the top, it goes in, so they cancel each other out. There is a torque. There is a torque.
How do you know that?
I said torque. What did you say? But how can it be a torque? Oh, so it was
How can...
Initially, we had sort of an even split. And now we have an absolutely overwhelming majority for choice number 2.
And that's not unusual that you go from 50-50 to almost 100%. I do show them that second distribution. So what is going on here? One, it's active, not passive. There's no way you can sleep through my classes, because every few minutes your neighbor will start talking to you. Believe it or not, some students complain about it and rather be sleeping. The other thing is there's now a two-way flow of information. It's not only from me to the students, there's information coming back to me. I don't have to wait till the midterm examination to find out, oh my God, they didn't understand this. It's right there and then in front of me. What's more, the students can test out their own knowledge. They press a button, they talk, they press a button again, and then they see the distribution. Imagine you're one of the students who is in that 10% who still got the wrong answer after the discussion. You're not getting punished for that because there's no credit for getting it right. You can press that button, take a risk without really being punished for it. But it gives you feedback on your own learning. And so many people have pointed out that feedback during learning is crucial. Normally, the feedback comes at the end in the form of a grade. This is what educators call formative assessment rather than summative assessment. Continuous feedback to the learner. So you want to try it? Yeah? You want to try it? Okay. Did you all read those notes about thermal expansion that were... No? You forgot. Oh, my God. That, a prerequisite is that you read before coming to class. Anyway, I'm actually happy you didn't read, because if there's one thing I miss about what I've done in education is that I don't lecture anymore. So I'm very happy that you're giving me this opportunity to lecture. I'm going to have to lecture you on the subject that I want to ask the question about. So I'll take a few minutes to tell you about thermal expansion. Thermal expansion. Materials, solids, expand in volume when they get hotter. That's true for all solids. It's particularly pronounced for metals. And it has a number of important consequences for engineering. For example, rails, the segments are never put together against one another. You may have heard that because when you're in a train, you hear this clickety-clack sound of the wheels going. You may wonder, why don't they just jam the rails together? Well, if they do, and the metal expands over long lengths of rails, pretty disastrous things can happen, as you see in this real picture that was taken somewhere in India. At some point, the rail is going to buckle and trains are going to derail. Likewise, for buildings that use steel beams, you have to take into account that the beams expand more than other solids and permit that to happen without plaster tearing and so on. So it's an important problem in engineering. Now, why does that happen? It happens because any material is made out of atoms, and as the material gets hotter, the atoms get further away from one another. So this is a cold metal or solid, but we're going to talk only about metals. And this is a hot metal. Cold metal, hot metal. That's all you need to know for this question. You may wonder why. Well, atoms, don't sit still. They move, they shake, they vibrate. And the amplitude of that vibration is what we interpret as temperature. So this is a cold atom, and this is a hot atom. Now imagine you're all atoms, right? You wouldn't just be sitting there, like you said. You would actually be shaking. Now imagine your neighbor starts shaking more. You get away from your neighbor, right? Atoms are like that, too. So, cold metal, hot metal. Questions, anyone? Questions?
Why do we need to know this?
Because it's on the test. Questions? I knew I gave a brilliant lecture, so we'll see how brilliant it is. Absolutely no questions? I mean, look, I'm not going to just blank out the screen and then ask you, when metals get hotter, the distance between the atoms, A increases, B stays the same, D decreases. That's not what I'm going to do. You have a question. The center one is not gotten hotter. Well, you don't see them shake because, oh, by the way, it's all of them. I'm only showing 9 atoms, but there are, of course, billions of billions of billions of atoms. So the center one is not moving. I mean, they're all shaking, but then you're very perceptive. The center one in this little animation here is not moving. Why is that? Is that essential or not? It's actually a choice. I just happened to pin it such a way that it's a center one that doesn't move. But I could equally well have taken the one on the top left. In that case, the center one would have moved to the bottom and the right. And the top one in the middle would have moved straight to the right. And the one next to it would have moved further to the right. The important point is that the distance between them gets larger, right? They all get further away from each other. Right? This one gets further away from that one gets further away from this. They all get further away from one another. Yes? So the question is it unbound if the temperature increases? Something interesting happens at some point. At some point, the atoms shake so much and get so far apart that they break loose from each other, and then you get a liquid. So at some temperature, with metals that won't happen under ordinary climate circumstances, but at some point the metal will actually melt. But we stay away from that. Yes?
If you added another ring of dots all the way around, would the distance from the center dot to one dot out be equal to the distance, would be half the distance from the center dot to 2 dots out? Does the expansion uniform?
Whoa, I'm not sure I understand that question. So I have a circle of atoms, right? And one in the center, right? So as I heat it up, that circle will get larger, right? And then the distance between the center one and one on there, I don't understand what you meant by 2 on the circle. Is that what you meant?
So right now you have a center dot and one dot that is one space away.
Yeah.
And when you heat the metal, that space between the center dot and the one at the edge becomes greater.
Oh, I see. So not a circle, but a square, basically. Yes. If I were to add a second, okay, very good question. Suppose I had added, we'd have not 9 atoms, but 16 atoms. 16? No, it would have been 25, right? Then those would have moved twice as much over as the first ring. Very good. Are you ready for the question? Okay. Now, notice that what I'm going to do is I'm going to take this and put it in a slightly different context, right? It's like the football and the baseball problem. But don't come to me and say, Professor, we've never answered that question before. Okay, so here comes the question. Consider a rectangular metal plate with a circular hole in it. When the plate is uniformly heated, the diameter of the hole, 1, increases, 2, stays the same, 3, decreases. And it's not just about the answer, it's about, why. So think, don't just click away. I'm going to give you enough time to think. Think. Shh, no talking to your neighbor yet. Let everybody think. And remember, atoms get further away from each other. Who needs more time to think? And it's fine. I'll give you more time. No? Okay, so what I want everybody to do now is commit to an answer. We only have 212 responses. There were more clickers have been handed out. So if you don't know, if you're not sure, make it a game, okay? But do press 1, 2, or 3, okay? Let's see. Well, we don't go much further. Okay, so, and now remember, you have to find a neighbor who has a different answer. So check with your neighbor, and then try to convince your neighbor of your answer. Go ahead. Remind me of the clicker at the end to announce that they shouldn't take him home. Look at that. I mean, look at it. You should see what I see from here. I mean, look at them there. They just can't stop talking. I mean, it's amazing. You know, you all got fired up. Probably by now, you have forgotten that I am here not to talk about metal plates. I'm here to talk about education. The answer to this question doesn't even matter. You know, I bet you're not even going to let me leave, right, without telling you what it is, even though... So before I tell you what the answer is, why don't you indicate what you now believe to be the correct answer? So if you had 2 and you have not changed your mind, you still press 2. If you change your mind, you press 1 or 3, and so on. Indicate what you now believe to be the correct answer. Okay. And while you do that, notice that in your discussion, it was not about the answer, but about the reasoning. In fact, I'm going to keep you in suspense a little bit longer here. And let's analyze this in a little bit more detail, right? One, you committed to an answer, right? And in case you didn't know it exactly, you pressed a button without being afraid that you made a mistake. Your future didn't depend on it. And even the students in my class, if they press the wrong button, it doesn't matter because, they're trying out their knowledge. They're not being punished for getting the wrong answer. Secondly, you externalized your answer. When you were talking to your neighbor, you started to talk about what the answer was and why. You moved from answer, fact, to reasoning. And lastly, and perhaps this is the most important point, is you became emotionally invested in the learning. Right? I told you again, it doesn't matter, but look I can feel the tension here, Now, I have some very bad news. Apparently, I am a really bad lecturer because only 21% got it right. And unfortunately, the method doesn't work well when only 21% gets it right, because that means that of the people around you, at least 4 out of 5 had the wrong answer. So I think I've already made a very important point. Even the most clear and brilliant lectures are not that clear. And I gave you all the knowledge you needed to know in order to answer that question. Let's see what the distribution is. And in fact, the wrong answer has gone up. That doesn't tell you what the right answer is. You want to know what the right answer is? I told you it doesn't matter because I'm here to talk about pedagogy. The right answer is number 1. Now, look at that. Look at the engagement. Look at how engaged. I do not want you to lie in bed tonight and think, why is it that number 1 is correct? Imagine you have a jar of jam. Look at how much attention you're paying. Imagine I'd just given a lecture on thermal expansion, and then instead of asking you the question about the hole in the plate, I would have said, when you heat a metal plate with a circular hole in it, the hole gets larger, and you would have written down, the hole gets larger. Would you have had this type of engagement? No way, right? It's the most mundane problem. And look at how engaged you are. Okay, anyway, jar of jam, glass jar, metal lid. The lid consists of a ring and a top. You put it in a refrigerator, take it out the next day, you can't open the lid. What do? You run the metal under hot water because then the ring expands. You think, well, that's unfair because there's metal at the top which pushes the ring out. Okay. Well, imagine we have a metal plate, no hole in it. We take a marker and draw a circle on the plate. Now, we put the plate over some heat source and the plate expands. What's going to happen to the diameter of the circle? It's going to get larger. You say, well, that's not fair. There's no hole. If there were a hole, the atoms would expand into the hole to get further away from one another. But wait a minute. Let's consider the atoms at the edge of the hole. We could go outside. I hope it doesn't rain anymore. We could go outside, all form a big circle. We are the atoms at the edge of the hole. There we stand. And now I tell you, take a step in towards the center of the circle. What just happened to the distance between us? It got smaller. It can't get smaller because, remember, your neighbor is shaking more. The only way to make the distance larger is to make the circle larger. You won't forget this. And probably you're again thinking, you've forgotten that I'm here to talk about education. I am here just to talk about education. Forget mental plates. It's unimportant. It's not going to affect your life in any way. So back to peer instruction. What is the result? Well, one is, and again, I wish I could show you data, but you can go to my website to actually download them. Higher learning gains, in fact, triple the learning gains in physics, and the method has been adapted in many other fields, and better retention. But let's get back for a moment to the lecture. What is happening exactly in a lecture? In a lecture, and you just had a few minutes of a lecture from me about thermal expansion, what happens is that you don't pay your utmost attention. In fact, in a very recent study done at MIT, some data emerged which are absolutely spectacular. They developed a wearable neural activity sensor which can be put around the wrist so that you don't have to actually have electrodes on your brain. And they had a group of students that they monitored for a week and monitored their neural activity, measuring motor activity, physiological activity, but also cognitive activity and emotional activity. And they plotted it as a function of time. Here's some data showing for 7 days, starting at the bottom was day 1, and then day 2, day 3, day 4, day 5, day 7, of the neural activity. Higher means higher neural activity. Now notice the sections that have been identified, class, and compare the neural activity during class to the neural activity during sleep. Only TV watching matches sleep. You're laughing about it. This is no joke. When you are a passive observer, and this has been known for many, many years, your brain activity goes down. It goes to alpha waves rather than really having something that is cognitively meaningful. So it's hard to pay attention when you're a passive receiver and not an active participant. And that brings me back to the beginning of my talk, because you all admitted you learn by practicing. And listening is not practicing. If you want to learn to play the piano, you don't just go to the concert hall to listen to Maria Piraia playing Chopin sonatas. You got to do the playing. If you train for a marathon, you don't sit in front of the TV eating popcorn watching marathon runners. You got to do the running, right? Same is true with any other discipline. After I had that 10-minute lecture, you knew it. It was so simple, the atoms getting further apart from each other. But that's because you've never been confronted with that misconception of what happens to that whole. And in a typical lecture, there is no opportunity to confront all of the misconceptions that occur in all of the brains of all of the learners. So you leave a lecture with this false sense of security. I know it. And I, as a teacher, left my classes, which I taught according to the traditional method, with a false sense of success, only to realize that it was all an illusion, a house of cards, right? False security with the students, and I had the impression that I'd done a good job, and my faulty assessment further reinforced that incorrect knowledge. So I want to leave you with this conclusion. Education is not about transferring information. And it's not about getting students to do what we do. We want to get students to go beyond what we do. We want the next generation to solve the problems we have not yet solved. There are plenty of problems. Energy, the environment, conflict, problems we don't know how to solve, but which future generation will have to solve. And active participation is a must. Just sitting there as a passive recipient of information is not enough. And I hope that I've illustrated that with a very simple change, peer instruction can help you to teach real problem-solving skills because it makes you comfortable with facing a problem you have not seen before. If that problem of the hole in the plate had been on an exam, on a high-stakes assessment, you would have come to me and said, that's an unfair question because you didn't tell us how to do it. Well, real problems, once you know how to do them, they're no longer problems by definition, right? But this is an opportunity to actually make students more comfortable with sticking out their neck and taking risks. and be more creative and therefore be more innovative. If you're interested in more information, that's the URL. You don't have to write it down. I'm very much against note-taking. Just remember my last name, go to Google, and then hit this I'm feeling lucky button, and then one more click and you'll have a copy of my presentation. One more thing. Those little clickers that you have in your hand, unfortunately, they don't control your microwave or your television. They're totally useless once you leave this classroom, so please return them so that the organizers will still smile at me afterwards. Otherwise, they're getting the bill. So thank you very much for your attention.